Hello. Right, let's get started. Just a little bit about me as well. I am the chief architect for Cloudera here in Europe. Europe and basically everything outside the US. And I'm also a patch committer for the HBase project in here, also on the PMC there. Written the HBase book, I had the opportunity to do so. And overall I'm quite binary, so I do things in pairs it seems. Like I have 2 cats, 2 dogs, 2 kids, 1 wife, but all in the know, count them as 2, right? I know, right? So to matter, I thought that's quite an interesting topic that I've seen at customers. And like this group, for example, I had this conversation a couple of times where new technology comes out. In this case, this is an example, Impala, but there are others. Ted gave a talk, someone else from the company gave a talk, Michael, a while ago on drill and other things. So there seems to be a need or some wishing that we should have SQL on top of no SQL, right? So this whole antimatter and matter coming together and sort of exploding the world. So I thought I'd give a bit of a talk about how HBase and a system on top of that can go together and if that makes sense or not. You can replace, as I said, these names that I'm using, you can replace them with other systems as well. They typically are quite exchangeable. So just because I'm using those now, doesn't mean it just really is all about that. So let's give a quick intro to HBase. So that's like slide 4 to 250. So okay, that's my introduction to HBase. That's HBase, right? So honestly, I mean, at least two good books about that. So please read the book. I can't really, honestly, in like 30 minutes go through and explain what HBase is. So for me, HBase, for you and us, HBase for this talk is this box. That's it. The point that I'm trying to make is that sure, we could try to talk about like how it lays on data, and I could go in like in a flame war with my friends from Napa here about what is better, which approach, right? So there's always ways of doing it differently, right? Overall, I think we all agree on this one. It's all about physics. So in the end, if you really want to achieve a good performance, you have to somehow solve this by either having really, really expensive hardware, or you have to solve it by trying to be smart about what you do with data, right? Trying to skip data, for example, instead of looking at everything, or storing it efficiently and make it somehow possible to go over data by not really touching every data, right? So there's the same over here. We're talking about this as well. So let's look at a little bit about the sort of the strengths and weaknesses of HBase. And weaknesses, I should have printed small there, of course. There are weaknesses, obviously. There's an open source project, so there's always things that we as committers and others as contributors work on. But the strengths really are that you have a random key value store. So you can store small values, key values, typically less than a megabyte even, randomly in a table. So that's a great concept, because with that you have like similar to a database where you have like columns and tables. It seems to map quite nicely. So we're already getting towards this. Why not doing this with SQL, right? If you look at Cassandra, for example, they actually have something SQL, they call this with a C though, not with an S. Where they say, well, users are obviously wanting SQL on top of our key value store, or big table clone, or whatever you call them. So somehow there seems to be a relation, because you have tables, and you have columns in there, you have rows, and somehow that's the same as in a database. Why not doing it that way as well? The thing with HBase is that it has a few other things built in, so it gives you a sorting, implicit sorting, by row keys and by columns. I have a slide on that one in a second. It adds basically the underlying concept, as I said, is more a typical key value store. This could be, for example, a Berkeley DB or something where you have true key value stores. Here you get this concept of this table with the rows and the columns, and it does this so somehow nicely underneath the hood by distributing it somehow over a cluster. You don't have to worry about this. You just store data in it. You have this logical concept of these rows. So that's quite nice and helps a lot abstracting the underlying layer. It also does something that comes out of its pedigree. It's basically trying to store everything sequentially. This is something that comes from log structured merge trees. There's some algorithms behind it. Nothing of that is new, that date back a little bit, a couple of years back. And when Google looked at what can we do to store data, small data points, they looked at existing technologies, read the papers, and thought, that might make sense. Again, it's all about physics. You cannot really do random seeking around on disks. That's quite slow. Disks have become larger and larger. They've grown in size. They also get faster overall. But they're really, when it comes to moving the head, there's a physical limitation. All about physics, right? So the head has to move around, try to find where the data is on those platters. The platters spin around faster and faster, but eventually when they go faster, the whole thing disintegrates and your computer explodes. I'm waiting for that one usually. But yeah, we'll go SSDs then, I guess, next. But there's a physical sort of limitation on those physical disks. So what can you do to actually be as efficient as possible? You write sequentially. So that's the whole idea. That was pretty much it. And they had like you need to somehow, if you write sequentially, you can't really update stuff that you have written before. So they came up with some sort of ideas of accumulating some updates first in memory and then writing them out over time, and then having some background operations to sort of do some housekeeping in the background. So this all dates back to. It's not really, as I said, rocket science, but it made sense because it optimizes on the physics of the disks by writing sequentially. Right, so back to the logical model. So if you look at what HBase does for you, it's like you have this sort of like table model, which means that you have rows and columns, and you have these indexes I mentioned. So you have on one side you have the primary index of sorts. That's the row key. That's that first column there. Row 1, row 10, row 18, row 2. Where you see that's strange. Why would it do that? Right, 2 is in between somewhere. It's all binary. Although I use something that you can read here, HBase really stores everything as binary. Basically, whatever you put in could be stored. It could be unprintable characters for all I know, right? But I chose deliberately here some that you can read, but it doesn't have to be that way. But it sorts them byte by byte, position by position, which is called lexicographical sorting, which means it looks at all the R's, they're all the same, and so forth, all the O's, the W's, the dash, and then it comes to the 1, 1, 1, 1, 1, and there's a 2, so 2 is higher, goes at the bottom. And then it goes to the next position. There's nothing, that is the lowest, and 0, 8, and so on and so forth. So it sorts column by column in a binary array, so index by index. What you can also see here, which is really strange, is that we do not have really like a database where you have one schema, which means you have one set of columns in the entire table, right? So it's different from that. You could have that. You could have a HBase table which has whatever, your street 1, street 2, or address 1, address 2, town, and zip code, and all of these things. Sure, you can do that, but you don't have to. Right? That's sort of one of the other strengths of HBase, is that it has this ability to be completely sparse. Sparse matrices or sparse tables are typically a problem with normal databases because they have to have these nulls everywhere, so you have to have a huge schema, and half of that, or say 80%, is never being used because some rows need this end of the schema and other rows need that end of the schema, but they never really overlap. So you have this huge schema, but it's completely warped depending on which row you're looking at. So for HBase, it's slightly different. HBase, because it's a key value store underneath the hood, what it does actually is you can create a logical view of this table, but name every column separately per row. So in this first row, I have a column A, B, and so on and so forth. And in the next one, I have others. So there's something missing, so there's no column B in the second row, right? Or I use a timestamp. I can use this is actually an int that I use there. And so it automatically sets that. And because I have, after my primary index, which is my row key, sorting that way, I also have this sorting horizontally inside each row per column name. So per column name here. So you can see, because they're ascending, I have the 23rd, the 24th, the 25th, and so on, sorted by date. I can make use of that one, for example, to store data that I need chronologically in order. Or I can use integer or long .next value minus the epoch, and then turn this around bit inversion on the timestamp, and then I get the newest entry first. For example, you store an RSS feed in each row. It's a separate RSS feed. But you always want to get the first 10 or the last 10 entries in an RSS feed. Use hosts of sorts. Then you can just basically use that reverse sorting and then just grab the first 10 columns. You're done with that row. Don't have to scan all the other whatever million of posts that have been posted before. If it's an active RSS feed, you don't have to do that. You just get the first 10 and you have what you want. You go on to the next row. That's quite nice. And that's all built in, right? So these are wrapping this up or summarizing this is that you have primary keys. They're sorted, like row key first. So it's only in one direction. And I didn't mention this earlier. You saw that when I had to reverse the date, I actually had to do this mathematical operation, like a bit inversion, to have that sorting the other way. That's the same for the row keys. If you want to have a table and say, oh, sort by, I don't know, by custom ID or by first name, and then also want to access this by reversely, by the other way around, you have to do this on your end in the application by storing this twice. There is no way of turning this around. No, there's no secondary indexing. There's some efforts to help with that, but nothing out of the box. So yes, a secondary indexing would be the option there. And the secondary keys are the column qualifiers or the column names that you saw earlier. That's my second index. Those two dimensions, so those two features, I can use to lay out data because I want to be fast in the end. The important part is everything that you store that way is sorted that way and stored that way sequentially. It means whenever you have a use case that needs data that is sorted next to each other, that is related, for example, a couple of columns or a couple of rows, and you want to access them together, make use of that feature. So create a key that keeps them together in the storage layer. So when you access the data, you're much faster because back to physics, you don't have to touch as many disks. Right, small weaknesses, as I said, a little bit. So HBase has a few warts as an open source system. It's not as professionally developed as other systems. It's in the open source world. It's I think one of the prominent tools. The drawbacks here is that because of all the developers of different companies working on this in collaboration, there's sometimes areas which get addressed quicker and sometimes a little bit slower. They all get addressed, as we have seen this in the past, but it takes a little bit of time. And what happens here is, for example, with HBase, that the underlying layer, talking to the file system and a few other bits and pieces, could be optimized. So it's not really as efficient. So back to physics, it's not only the disks that you have to be concerned about. When you use a system, any software system, what does it add in terms of delay? Like what's the latency of the system? And there is a little bit of latency if you add HBase on top of, for example, HDFS. There's more moving parts, more threading, more I/O, more blocks being pushed around. All of that accumulates, and you will have a slow performance. Again, you have to decide what you do with this. And there's a couple of other things, like there's a single rider. So write performance is okay, but if you were to put it at top speed, the single rider headlock that we currently have is a bit of a hindrance. All of these things are currently addressed, but you have to think about that. Right. And then there's this dilemma. So I sort of put this in really easy terms, like this is the easiest sort of chart that you can think of. HBase can cover quite a few use cases, but depending on what the use case looks like, you have to do things differently. So sometimes you have to lay it out that way, and sometimes lay it out that way. And sort of the two opposite ideas in HBase that you can actually implement are these two, either events or entities. So as an example, for events, it's time series data. And on the other spectrum end, basically, is the message store, or like the thing that happens continuously. So these opposite use cases, the entity store, think of it as a message store, like Facebook messaging, for example, is a good example of this one. And there's a couple of other use cases that use HBase for that purpose. The problem here is that it always updates something. All of us, like you, me, we all receive email every day. We read an email, we write an email. All throughout the day, our inbox has some churn, right? Something happens in our inbox. which means the entity, our inbox, gets updated constantly. Over time, gets updated and updated. Right? That's okay. The problem is that underneath the hood, the way these data is stored, it has to be stored in files. All these files on disk will have some data of our entity, of our inbox. Because I'm writing something, I get an email today, that gets been written out and it's persisted, then I get another one, I don't know, an hour later, as I say, tomorrow at 1 a.m. I get one, and then at 2 a.m. or 3 a.m. So every hour I get one email coming in. And they get sort of pushed out into the history of the entity. To read that inbox, to recreate the logical view, I have to actually look at lots and lots of files. Again, back to physics, bad idea, right? So we don't want to do this. But this is like the one end of the spectrum. It means the entity store example is often a problem with performance. You have to be careful to lay out the data right and making sure that it actually performs the way you want it to be. On the other hand, the event store, that's, for example, on my RSS feed. I get an RSS post from like this one, I would say, I don't know, /dot, whoever remembers that, /dot, basically giving me an update I go a couple of minutes, a post comes in. I just write it out and will never touch it again, right? Or I just read it, basically, that's all I do. But the older stuff, I probably never really go back and look at what happened, like, I don't know, a couple of months ago. I might search it, that's a whole different exercise. But I don't really want to see what happened the last couple of minutes, like Hacker News. The first page you see is the most current events. So you store them, you saw that how you store them with the reverse timestamp, and then you can just grab that and show that. But the point here is it doesn't get changed. So data now is basically only in one particular temporal spot in my storage, so I can find this quite efficiently. On the other hand, the write pattern might be disadvantageous or not really advantageous, because if you write sequential data into a sequential store that needs to sort and therefore serve data in a way that a specific server is responsible for a range of rows. If you hammer that server, the problem is that you're only getting the performance of one single server, not the full power of the cluster. So you need to somehow get the keys and distribute them by hand or manually somehow, or with hash keys, bucketing over the server. So the event store example gets you at the right time. Right. Let's have a quick look at Impala, just to give you sort of an idea of where this comes from, why Impala, or as I said, any other of these systems that want to bring SQL and low latency queries to the Hadoop data, right? So this is an example of that. The overall idea is quite obvious, right? So you have MapReduce, which is in itself a batch system. So batch systems are okay, they scan sequentially, they're quite fast once they get running. The problem is if you have BI tools that do small queries, they're not really great with that, because they have, if you wait for a batch job to wake up to find a couple of data points somewhere and return them to you, and you wait for a Java program to start, this is going to be costly. So you want to have something that has lower latencies and is faster. So the whole runtime startup overhead is not something that you want to have on short analytical queries typically. So again, Google, invent of Bigtable, invent of the file system, GFS, and other things. They created that basically and published the papers on that. As I said, a lot of these technologies are based on previously existing technologies, but they were clever enough to put them together and make them work. They came up with Dremel. Dremel was sort of their power tool name. They had all of power tools there. The idea was that we lay out the data in an efficient way that if I search for something very specific, that the file system or the file format can tell us where to look for that data. That's very much what you, if you remember earlier, physics again. You don't want to look at a lot of data. So if you look at that code, they can do a trillion row in a few seconds. They're not touching those trillion rows in those couple of seconds. They're really efficient because they do aggregation and typically quite queries that are highly selective or very selective, which means you can skip a lot of data that you don't need. So the file format underneath tells Dremel, okay, all of that data, don't want to have it, just skip it, don't even read it. Like, go forward, go seek to the next one, or somehow ignore that data and therefore be much faster. This again just boils down to physics. You want to ignore that data. So they have this column of storage format. There's an open source implementation of that called Parquet as an example, and that helps driving the speed of those queries. So the goal is really for Impala in this case is we want to have SQL on top of data stored in my Hadoop ecosystem. All right. The first one was obviously HDFS, so we can scan text files, but of course Parquet files in the future. That's support for it there now. And so we want to somehow do the same thing as Dremel did. But if you have a storage layer, or like a query layer, called, like it has SQL support, and you have a storage engine called HBase, for example, that has also data, it obviously makes sense to marry them somehow, right? So why should I only query HDFS data, but also data in HDFS? So the way this works is basically, just as a background, the queries are sent to the servers. We'll look at this in a second, how this works. They get C++, the query gets translated with LLVM into machine code. The LLVM optimizes the query, drops loops and stuff like that, unwraps the query, and most efficiently runs over data. So why isn't that fast? That should be always fast. I mean, if this is C++, it's much better than Java, right? It's the age-old sort of discussion, what is the faster programming language? Which you know it's not true, right? But I'm just saying, C++ gives us a few advantages being closer to the operating system. Right? Two daemons, similar to what you see in other systems as well, like be it HBase, be it HDFS, be it the old MapReduce or even Yarn. Typically you have a worker node and you have an orchestrator. Here you have a worker node, which is the same on all of the nodes that have data, and you have a metadata cache, which is the state store. So how does it work? Let's look at this. So we have all of the different components here. These are 3 nodes at the bottom, 3 physical computers, like servers sitting in a data center. They all run the Impala daemon here in this case, and on top left you have the actual application asking for something in the minute. And on the right hand side you have the metastore. Impala shares the same metastore as Hive, so we can just basically, whatever you do in Hive, you can also do it on the Impala side, which makes sense. And they every now and then sync up with that metastore. Now here comes the application, says, here's SQL count star from, I don't know, users, semicolon, important. Right, so they ask you this question, and somehow the system goes, oh yeah, here's a work. Lands at any of these nodes. I just picked the middle one here, coincidence. It says, okay, right, what we do with this, let's send this out, the coordinator, the planner breaks up the query, sends this to the coordinators. They say, okay, where is that data local? Again, physics, don't want to touch the network, because this is the worst thing. I mean, seeks already are bad on a disk, but if you then touch the network, yeah, it's into a whole different realm of slow in comparison. Right. So where does the data sit and therefore send the data or the queries over? So it reads locally on all of these, streams back the data back up to the client. All of this is very local, very logical. The interesting thing is the node on the right hand side. You can see that it actually reads from HBase, not from HDFS. So actually this query sort of branches out into multiple things. So there's maybe a subquery or something that says that fact table or that user table, which is quite small or whatever it is, sits on the HBase side, so it has to read on HBase as well. On these other two, they read from HDFS. Why not? Right. Now, how do we get this together? Why isn't this like a generally good idea? First of all, you have to map types to binaries. Remember in the beginning when I gave you that like 236 slide introduction to HBase, or it was like 1 or 2 slides. But the point is that everything is binary. That's the one takeaway. Everything is binary. Now, how do you map this into a metastore that has types, right? That's where a mapping comes in, where you have to combine the two and say, okay, binary keys. How do I translate them into something that the SQL side can understand? Because there you have types. You want to talk to it, right? The important part, important takeaway here is that it shares the same metastore, so you only do this once, on the Hive or on the Impala side, and both can use this. And then you have to map the columns of HBase into Hive, and we'll look at this in a second, or in Impala. Impala prefers the string type for the key, just for the row key. You remember there's lexicographical sorting, the row 1, row 10, row 80, row 2. It tries to get around this by saying, for now, let's use a string, because the string is easier to compare, then we get like natural sorting order, a bit more something that we can expect. Right, so how does it work? We define a schema. Here we just create a table. It's just like a normal table as it would for any other data stored in HDFS. You create the table. You have two fields, a key and a value. But you hand in a bit of a ugliness there, which is like a full-on specified class name, or class with path and everything, packages in the head of it. The HBase storage handler. That's actually the translation of everything. And there's two extra information here with sturdy properties and table properties. So that's where you actually do the mapping, right? So really the important part is this. So we're mapping key and C, column family 1, value 1, to these two fields on the Hive side. So what you see there is like, oh, there's a column key. I don't have a column key in my system, so how does it, why a column key? That's actually a special notation. That means whatever my key is, my row key, that's fixed on the HBase side, map this to that field over there. And you can swap them around. You can actually do this reverse as well, but that's how you map them together. You have a couple of options. You can either do a new table, where you create them on the Hive side, and they end up being created on the HBase side. But there's nothing really configured on these tables, right? And the other thing is you can actually create an external table. That's very, very useful. We already have a HBase table with data. You do this with an external table, and you point to it. What are the further options? I talked about column mapping. That was the thing that you just saw, where you have the list of HBase columns and how they map over. No spaces, just as a hint. If you have spaces, that's actually going to fail, because spaces could be, because it's all binary, a valid character, as a hex 20 or something, a 32. Therefore, don't use spaces. Right? We could trim them, but then we might actually have a column in HBase that ends with a space. Could happen. So no spaces or intentional spaces. The key mapping is the special one, and then you can map any column over into HBase land. Right? There's two notations with binary and string. The old one was string. Now you can actually use binary, which is the same thing as what we do on the HBase side. If you're familiar with HBase, there's a bytes class that you can use to translate double and int and stuff like that into something binary. That's supported here as well. So Impala or Hive would decode this with the right classes into the right types. What are the limits? You can only have one key, obviously, because this is only have one row key per row. Therefore, it's only one special column key. Yes, you have to place it somewhere, but you can shuffle this up whatever you want. We don't have any access to versions. As you remember, I didn't mention this, but HBase is actually a multi-dimensional store. It has a time component. Every key value is stored with a timestamp, and you can keep multiples of those. That's not passed on here, so you can't really talk to it. So again, some limitations that you have to work around or ignore. You always get the latest. You don't have to map all of the HBase columns into Hive or into the meta store, but those that you don't map, you can't access. Makes sense. Why would you see them? And then there's some weirdness if you're used to a normal Hive insert, for example. If you use Hive and you insert something, insert override typically replaces everything that was previously there because it's a file operation. Here it's slightly different because HBase is, after all, mutable. That's the whole idea, that you can do random updates. If you do an insert into HBase, then stuff gets replaced or doesn't get removed. So be aware of what happens underneath the hood. Right, final part. Let's have a quick look at when you actually look at the data. This is quite ugly, it's all shell stuff. The first operation there does a list. We have one table, that's the one that we defined, or that we had earlier, XYZ. This was on the table properties there. If we describe XYZ, we can see the created CF1, that's the column family that we specified in the mapping. And then we can scan and nothing's in there, right? So it's like there's a scan at the bottom, scan XYZ, and it's counted and it's actually empty, right? So now we can actually do on the Hive side or Impala side, do an insert, like inserting something from, there's a POX table, this comes out of the standard manual for Hive with HBase, so you can actually try this on your own. All of this works. There's a demo file, POX, it's called, that comes with it, and you can use that. And then on the HBase side, we can do a scan, and after we have done this insert, you can see there's one row that we just inserted with that one key. Right. Pro tip, and I think my friends again from Member agree, that's a great tool. U is the front end. If you don't want to do this ugly shell thing, you want to see what's in your table, what are the actual columns, and how many rows do we have, and things like this, please have a look at U. It's a nice interface over data stored in HDFS. Right, so the final part is, I mentioned you want to have data stored next to each other. Because of the physics, you don't want to jump around on a hard drive finding data. You want to have it stored together. And the way that HBase does that is it uses a scan object. That, if you're familiar with HBase, is the sort of go-to class to scan a couple of rows together or a couple of columns together. It has a feature called start and stop row, which are quite efficient because that will limit how much data you actually scanning through. So if you can use start and stop rows, it works, but it only works on the primary index, on the row key. And then you have server-side filters that you can issue. You can filter certain rows out, but they don't help that much. Only certain do. And you have scanner, batching, and caching. So I'll skip this one. On the Impala shell, same with Hive, you can actually push some of these configurations into the scan object from the outside to help out a little bit on certain features. Back to physics. So that's second last, I think. A scan can only be really fast if you skip or read as few data as possible. That's the whole takeaway of this talk. So how can you create an SQL front end through a tool talking to a NoSQL database and keep that in check? That's the important part. And there's it requires really to have the right schema, and there's two use cases, OLAP cube and time series. Just wrap things up, is if you're interested in that, have a look into Facebook Insights. That's one where they keep an OLAP cube live. They're using counters and HBase, counting everything that happens on the web live as it happens. And then when it comes to query time, all I have to do is grab a single row in HBase. No like seeking around. It's a single piece of data, reading it in as one block load, and then you're fast on that end. They do take a bit of a hit on the right side because they have to somehow create all of these counters and insert them. So that's basically an interesting system. What I mentioned at the bottom is, I think what will happen in the future is that and I see this at customers as well, talking to them, we more and more go towards a hybrid solution where we have complex event processing, maybe HBase and maybe HDFS together. So because if you look at this system, it's only driven, like the Facebook Insights, only driven by HBase. But Facebook also stores all raw events on HDFS for further batch processing. So they already have a hybrid system of sorts. And I think we will have, or will use something in the future here as well. Final example is time series. I mentioned this, that's the other end of the spectrum. OpenTSDB is one here that comes to mind, which writes the metric first and then basically a timestamp. So they get some distribution over the cluster, which is quite good. And then doing reading, they're reading data for a specific metric. So if they create a graph, how much CPU did I use? They go for the metric ID of the CPU usage, and then they read time-stamped data that is sorted next to each other. So again, very efficient, right? So that makes sense. So bottom line is to really combine an SQL front end with basically an SQL engine with something like HBase, for example, is that you have to make sure that you query it the right way. So you have to make sure, for example, that your where clause has to contain the row key, that thing that they had as column key. If you don't use this, don't say where this is, say where the key is greater than that and less than that, for example, where you can set a stop and start and stop key at the scan, then you have to do a full table scan. So whenever you implement something over HBase, for example, through SQL, and it takes ages, it's dead slow, like as we say, right, oh, this is slow, it's too slow, should be fast, it's only a couple of rows or a couple of data, it takes ages. That's when you have done a full table scan. That's typically you have to change your design on the HBase side to move what you need into the key and be faster. And finally, future work really is, I see this as that we need composite keys. You remember the OpenTSD example just then? It has the metric ID first in the row key and then a timestamp. That we can't currently sort of carry over into Hive or into SQL. We need to be able to split them out and say there's one part of the key which is the ID and there's one part which is a timestamp. Then we can do better queries on that one and hopefully translate them back into something more efficient on the HBase side. And then expose the key value versions I mentioned, also important, and even be better at pushing down things towards the database. But as I said, in the end, all this goes back to all this physics. You need to somehow design the schema in a way that you most efficiently scanning over data. Don't touch everything because that's going to kill you. Any questions? Oh, Ted. Very good.
So you use OpenTSD as an example.
Yes.
And you mentioned composite keys, but they also have composite keys where the actual value and key and value are both in the key.
Yes.
And they also have 3,600 and a few columns.
Mm-hmm.
How would you address that?
With this schema, that's impossible. That's too specific, that schema. So you wouldn't be able to do that. So what they do is like the timestamp is a bracket, and then every column has the delta to the timestamp. So they're adding the timestamp of the column to the bracket, to the base time in the key. So the key would be, for example, timestamp, or second one, and then the other one would be 2, 3, 4, 5, 6, 7, and so on and so forth. And then the next row would start with, for example, epoch 100 or 366 or whatever the value is. So that, I don't think you can translate.
And then they have compressed columns. So,
yeah.
But this is the reality of most stage bases,
exactly.
right?
Well, no, this is a very specific schema that optimizes on the HBase side. So I guess that's the takeaway of this one is that there are quite a few schemas on the HBase side that you will not be able to press into SQL. You will have trouble with that because you cannot really translate them easily, right? You could then simplify on the SQL on the HBase side, but this might come at a reverse effect. There wasn't. Sorry. Yeah. Other questions?
In general, what's the difference between Architect and HBase? Both are no skeletal.
No. The question was, what's the difference between Parquet and HBase? Parquet is a pure file format. It just stores data in an efficient way. There's no server on top of that. It's just a binary file format, like how the data is organized in the file. So you could compare Parquet with what's underneath HBase, which are called, these files are called H file. Like the H file that we have as a layout compared to the Parquet file layout. Parquet was developed really as a sort of an analog to column I/O that Dremel has. It's very efficient in storing nested data structures. They use protobuffers, and on the Parquet side we use Avro to serialize these sort of nested records very efficiently, storing them all in columnar format. That is not really ideal for the HBase side because HBase has a few other simplifications. So there's overlap, but not really. Often you have to choose one over the other.
Okay, let's move the rest to the break, and let's have a 10-minute break and take a cigarette. And so thanks to Lars for giving this talk.